qubits. If each qubit is in either ket0 or ket1 state exactly, then there are a total of 2 power n combinations. Each combination is thus some state of the composite n-qubit system. A sequence of n bits encodes some number in the binary number system, and we can use this number to order all these combinations. So, for example, the combination of all zeros is the first combination, and the corresponding number is 0. And the last combination is where every state in the ket1 and the corresponding number is 2 power n minus 1. And I'll explain in a moment what those tensor product means. And this notation is just a shorthand for this notation. This set of states form the so-called standard or computational basis of the complex Hilbert space of all possible states of a composite system of n qubits. So this is just a linear complex space, and this is its basis. Okay, now in general, if we have two vector columns, then we can define a tensor product of these two vectors. And what we do here is we take the first element of the first vector and multiply it by the second vector, one by one by coefficients, and put it at the top. And then we take the second element of the first vector, again multiplied by the second vector, and put it next to it, and again until the end. As we can see, the total size of the tensor product is the product of the sizes of this vector. So it's k times L, the size of this vector. Note that the tensor product is linear in both arguments. So if the first vector is some linear combination of two vectors, and we take tensor product with some other vector, then it will be equal to this sum. So where we can just expand this sum. And similarly, for the second vector, we can expand also in the similar way. Okay. Now, as was mentioned by Andrei, this basis states of the single qubit, ket0 and ket1, can be represented by these vectors. And so when we take tensor products of them, what we get is these large vector columns. And in fact, for every basis state, there will be only a single one, and the other elements will be 0. And moreover, this one will be exactly at the place that corresponds to the number that this sequence of bits encodes. And so what we have is that the order that I introduced before of these vectors, of these states, it actually matches the natural order of these vectors. Note that such vector columns also can be thought as matrices of size 2 power n times 1. Now, every state vector of a composite system of n qubits is actually a linear combination of basis state vectors. So every state is this linear combination, and which can be also written as a vector column. And we have here 2 power n complex coefficients. And we also require that sum of the squared modulus of those coefficients equals to 1. And you can see that this is there is a huge number of coefficients. So, for example, if you have 50 qubits, then we need 2 power 50 coefficients to describe a state of a system. So this is almost practically impossible to do on a classical computer. And that's why the simulation of quantum system is so hard in practice. And just like in the single qubit case, the result of the standard measurement of a system in this state will be the label I with the probability pi equals modulus alpha I squared. And in such a case, if we see the label I in the measurement, the post measurement state of the system will be the I's basis state. So if we saw label 1, then the post measurement state will be this basis state. Now, if in a composite system, a state vector can't be written as a tensor product of 2 vectors, then it is called entangled. For example, let's take a 2-qubit system and take this state. It's ket plus tensor ket plus. It can be expressed in this way. So we just write down what ket plus means, and then we just use the linearity of the tensor product, and we can rewrite it as this form. Now, it is not entangled because it is a tensor product. And we also call such states as product states or simple tensors. Also, these states are separate. On the other hand, we can take the so-called Bell state, which is this state on a 2-qubit system. And this state cannot be written as a tensor product of 2 single qubit states. So we can't write down this formula. There is no such coefficients exists. And this is actually not hard exercise to prove by yourself why they not exist. Now, as was mentioned by Andrei on the previous talk, unitary operators are what model what happens in the physical world when we apply some operation on a physical quantum system. Well, there is actually 2 main different types of operations. It is unitary operations and measurements. Now, here we talk about unitary operations in a bit more abstract form. Now, suppose we have some complex Hilbert space of dimension k. Then a unitary operator is just a linear operator that can be defined by this formula. So we just take a u times a adjoint of u and this should be equal to the identity matrix. Equivalently, there exists the inverse matrix or operator of U, and it should be equal to the adjoint operator. Now, I recall that in a matrix form, the adjoint matrix is just the conjugate transpose of U. So if U has this matrix, then the conjugate transpose is to compute conjugate transpose, what we need is to transpose this matrix, all right, and take conjugation of these complex numbers at each entry. The important property of them is that unitary operators actually send any orthonormal basis of this space to another orthonormal basis. And this is actually their defining property. So if A1 and so on is some basis of H, or of our space H, then the images of these elements under the operator U form some other orthonormal basis of H. And on the other hand, if we have some two orthonormal bases A and B, then we can define operator by this formula, and it will be necessary unitary, and it will send the basis A to the basis B. Now, if U is unitary, then inverse operator, inverse matrix is also unitary, and the product of two unitaries is also unitary operator. So, in fact, the set of all unitary matrices or operators, they form a group. And also important property is that the spectrum, I mean, this is the eigenvalues of unitary operators are unit complex numbers, which means the modulus of those numbers are 1. Okay, so. Okay, now I can formulate what is known as a no-cloning theory. This is a very famous result in quantum mechanics, and it has a fundamental importance. In its simplest form, it states that the following: there is no 2-qubit. There exists no 2-qubit unitary operation U such that it sends tensor the state ket psi tensor ket 0 to the state ket psi tensor ket psi, possibly with some global phase, which can even be dependent on this state. And we require that this formula should hold for any 1-qubit state psi. And this is the mathematical formulation of the cloning of the state of a qubit. Right? So here we have psi here and ket 0 here, and here we have 2 psi. And the theorem is that there is no way to actually implement this. And the proof is actually simple. We can actually just take psi to be 0, ket 0 state, and psi to be ket 1, ket plus state, and using this identity, compute the scalar product between these two vectors, and then we can see the contradiction. Okay, what we need next is the product of the tensor product of matrices. suppose we have two matrices A and B, complex matrices, and they are not necessarily square. They can be some general matrices of the sizes k times L and p times q. All right. Now, the tensor product of those matrices is the following matrix of this size. So this is a block matrix, and what we do is we take each element of the first matrix and multiply it by the whole second matrix, and then we expand all the blocks. After we expand all the blocks, we will have this large matrix, and its size. You can see that the numbers of rows the number of rows of this matrix is actually the product of the numbers of rows of this matrix and the numbers of rows on this matrix, and similarly for the columns. Now you can actually, it's not hard to see that the tensor product of vectors that I defined before is actually a special case of this rule. And this tensor product of matrices is actually also linear in the first and in the second argument. We also can define tensor products of more than two matrices simply by sequential application, right? So we compute tensor product of these two matrices, then tensor product with the second matrix, this third matrix, and so on. And when we calculate it, we don't have to worry about the brackets order. So this means that the tensor product is actually an associative operation. But the tensor product is not a commutative operation, so the actual orders of these matrices AI matter. So we can't just permute the matrices in general. There is a useful the so-called mixed product property of the tensor product, and it states the following. So if we take tensor product, one tensor product of matrices and the second tensor product of matrices, and multiply them as simply as matrices by the usual matrix product rule, then it will equals to the tensor product of matrix products. And this holds, of course, only if the sizes of matrices A and B are compatible. So in general, they are rectangular matrices, and we need to be able to multiply this matrix by this matrix. So the number of columns and the rows must be compatible. In particular, if you take the tensor product of matrices and the tensor product of vectors and apply this matrix to this vector, then the result will be the tensor product of applications of these matrices and these vectors. And again, of course, the dimensions must match of these matrices and these vectors. Using this property, one can show that a tensor product of unitaries is also a unitary matrix.
Okay, I see question. There is a question,
yes.
You can answer it.
Okay, so can we clone the state by non-unitary transformation? This is valid for all linear operators. So there is no way, so even if we try some measurements, there is no way to clone it if we don't know the state. So there are many generalizations of this theorem, and the most general form is very, very powerful. So there is no way to clone the state. Yeah, but there are very big generalization. Okay. Now, what is multi-qubit gates? An n-qubit gate is just a unitary operator U that acts on a state of a system of n qubits. And so it can be represented by a matrix of size 2 power n times 2 power n. And this matrix is usually considered in the standard basis. For example, let's take a 2-qubit system. And the simultaneous action of Pauli X on the first qubit and the Pauli Z on the second qubit is the following unitary. We just take the tensor product of them. So it's X tensor Z, and we can write down these matrices and apply our rule, and this will be this block matrix, and we can expand to obtain this matrix. And this will encode this action. But actually, this gate X tensor Z is the product of two gates, of two such gates, and where I is the identity matrix. And again, you can see this by the mixed product rule. Now, the gates like X tensor I or I tensor Z, even though they are formally acting on 2 qubits, they are considered to be single qubit gates because no action actually happens on this other qubit. So something happens only on a single qubit. And physically, we also mean it means that there is nothing happens to this other qubit if the action is trivial. So the action is just identity matrix. And similarly to the notion of entanglement of states, we have that not all 2 qubits gates can be written in this form. So in this form, there are gates that cannot be represented as a tensor products of just a single qubit gates. And a prominent example of such 2-qubit gate is the CNOT, controlled NOT gate, sometimes also called the CX gate. It can be expressed, defined by this expression. This is a projection on ket 0. So this is just matrix, 2x2 matrix with a single one, and the top left corner. This is identity matrix, and this is a projection on ket 1, and it will equal to this matrix. Now, the action of this gate in the standard on the standard basis is the following. So the ket 0, 0 goes to 0, 0, 0, 1 to 0, 1, and those two actually switches. And as we can see, if the first bit is 0, then nothing happens here. But if the first bit is 1, then we flip the second bit, right? Like here and here. So we apply the NOT operation. And that's why the naming, the controlled NOT operation. And we also call the first qubit as a control qubit and the second qubit as the target qubit. Now, a quantum circuit is a graphical representation of quantum gates and other operations that act on a state of a multi-qubit system. For example, consider this circuit. What we have here is that there are 3 lines indicated that we have 3 qubits. This means that the initial state of this system, this 3-qubit state, is some ket psi vector state. Then some unitary action happens on to this state, and in the end we perform a measurement of of the resulted state, the standard measurement. Also, usually by default, we think that the initial state is just a ket zeros vector. And then this is what I say. So another example, consider this 4-qubit system. Okay, the initial state is ket zeros, and then what we do is we apply the unitary operation U1, then U2, and then U3 in this order. So on quantum circuits, you may think that time flows from the left to right, right? So here was the state, then this action happened, then this, and then this. It is important to note that mathematically we actually write it in the reverse order. So the final expression for this state will be this one. So we at first we had this state ket zeros, then we acted by U1, then by U2, and then by U3. So this is an important distinction that you should you better remember. Now, if a quantum gate acts non-trivially on some qubits, then we draw it only on them. So, for example, consider this 3-qubit operation. Now, we can, again, we can express this as a product of 2 unitary gates, unitary matrices, and we can see that in this matrix, the non-trivial action happens only on the 2nd qubit. This is a Pauli X action. So we can write it simply as this X gate on this 2nd qubit. And here we have action H on the 3rd qubit. So we write it like here. And here we just don't write anything. So this circuit actually equals to this circuit. The controlled operations is an important class of quantum gates. The basic example is what I already mentioned, is the CNOT gate. And it has a special depiction on quantum keycloaks like this diagram. So here we have the control qubit. The first is the control qubit, and we denote it by this. And the 2nd qubit is the target qubit, and we denote it by this symbol, and also we draw the connector line. If we have n qubits, then we can define a CNOT that acts on the qubits k and l, where k is the index of the control qubit and l is the index of the target qubit. So, for example, suppose we have 4 qubits indexed by 1, 2, 3, and 4. Then CNOT 4.2 will be drawn as this circuit, where we show that this is a control qubit and this is a target qubit. And what this operation means is that we have the following identities. So for any classical bits B1 and B3, we have this. We can write these equations. So if the fourth bit is 0, then nothing happens, right? And if the fourth bit is 1, then we flip the second bit. So this element, this standard basis element becomes this. And similarly here, since this here we have 1, then we flip this value. So this becomes this standard basis vector. So this operation actually permutes the the vectors of the standard basis. And since there are 4 qubits, it will the matrix will be of the size 16 by 16. Okay. We can also control by value 0 instead of value 1. This is and in this situation we will have the following gate. So we can define this gate by this expression, and will be this matrix, and its action on the standard basis will be the following. So if the value of the first bit is 0, then we flip the second bit, right? Like here or here. But if the value is 1 of the first bit, then we do nothing. So nothing happens. And that's why the naming controlled by value 0. And we draw it. We draw this gate by this picture. And it is actually not hard to prove that this gate is actually equivalent to the combination of this combination of gates. So I recall this is X tensor I, right? This is a usual CNOT gate, and this is again X tensor I, and you can verify that this matrix and this matrix, 4x4 matrices, are equal. If you have for some general 1 qubit gate U, some unitary matrix of the size 2 by 2, then we can define its controlled version that acts on 2 qubits. It's controlled U. It can be defined by the following rules. So if the first bit is 0, then nothing happens. But if the first bit here is 1, then we apply the U action on the value of the second qubit, like here or here, right? So the value 1, so we apply this unitary operation on the state of this qubit. Also, this same operation can be write in this form, and it will be the following block matrix. And you can expand, if you expand this matrix, this is identity. If you expand these blocks, it will be just a 4x4 matrix. And its circuit representation is the following. So similar to the controlled operation, we write this is a target, this is a control qubit, and this is a target qubit, and we put this U action here. And it's actually not hard to see that the CNOT operation that we talked about before is actually the controlled version of X. Okay. Similarly, we can define the controlled version C controlled U for multi-qubit gate U. For example, let U be any two qubit gate. Then the controlled version will be a 3-qubit gate that can be defined by these expressions. So again, if here what we have, psi is some 2-qubit state on qubits 2 and 3. And if the first qubit is exactly 0, then nothing happens. And if the first qubit is exactly 1, then we apply this unitary U on the state of the second of two last qubits. And again, we call the first qubit in this situation, we called the first qubit as a control qubit, and the last two qubits, 2 and 3, are the target qubits. And we draw it as the following circuit. Now, a quantum register is a subset of given qubits, which are just grouped for convenience. So, for example, we can split n qubits into two registers of sizes m and n minus m qubits. On quantum circuits, this can be drawn by this way. So, well, 0m is this is just a string of m zeros, and instead of drawing all m lines, we just draw this crossed line, similarly here. And so the previous controlled gate could be depicted as this diagram. So instead of writing this circuit, we could write this circuit if we don't need all the wires to consider. We also can control gates by many qubits and not just a single qubit. The basic example of this is the CNOT gate. This is a controller-controlled NOT gate, and it is also known as a Toffoli or CCX gate. It is a 3-qubit gate, and it can be defined by the following rule. So again, when we apply here, what we have here, B1, B2, and B3 are some bits. So this is the basis state. And the result of the application also will be some basis state. Here are some bits. And nothing actually happens if the first 2 bits are not exactly 1 and 1. But if the first 2 bits are exactly 1 and 1, then the third bit here becomes we flip the third bit. So we apply the NOT operation. And so hence the naming controlled NOT.
Dr. Yakymenko, we have 10 minutes till the end of the lecture.
Thank you. And since this is a 3-qubit gate, the corresponding matrix will be of the size 8 by 8. And on a circuit, it is represented by this picture. So here we indicate the two control qubits, and this is the target qubit. And it is actually not hard to verify that this CNOT operation, controlled NOT operation, is actually a controlled version of CNOT. As I defined before. So we can simply write down this circuit identity. Now, similarly, one can define multi-controlled versions of multi-qubit gates, which are controlled by many qubits, and where control can happen by the values either 0 or 1. For example, let's look at this circuit element. What we have here are 6 qubits. On the first 2 qubits, there is some action of a 2-qubit unitary, but it is controlled by these last 3 qubits. Now, and this means that, for example, this basis state will go to this state under the action of this unitary. Why? Because this last 3 bits, 0, 1, 0, 1, it corresponds exactly to those depictions, right? And since they correspond, we apply this action U on the first 2 qubits here, and this remains the same as here. And if the last 3 bits has a different pattern, then the action would be just trivial, so nothing would happen. And this is also a matrix of the size of. You can write down this matrix, and this matrix will be of the size 2 power 6 times 2 power 6. The swap gate, also an important gate of quantum circuits, and can be defined by this rule. So it is actually swaps the bits. So if 2 bits were 0, the result will be the same, and similarly for 1 and 1. And if here we have 0, 1, then the result will be 1, 0, and similarly here. So we just swap the bits. And we can write, we know how it acts on a basis, so we can write down the corresponding matrix. As you can see, it swaps the corresponding vectors. Now, in fact, we actually can use linearity of the tensor product and prove that for any single qubit states U and V, this swap operation actually swaps this tensor product of these 2 vectors. So U tensor V becomes V tensor U for any qubit, for any states U and V. And its depiction on the circuit is the following. So here we have there are no some control or target qubits. They actually have equal rights, let's say. And this is a representation, and it can be shown that it is actually equals to this circuit. So just the product of 3 CNOT gates, where this middle gates is reversed. So it can be. This is some very nice identity. The control at Z gate, as I was defined before, is the following. Will be the following matrix, and it has, due to its significance, it has the following special depiction on quantum circuits, like this one, and it is symmetric because there is no difference what the target and what is the control qubit, because this operation and this operation are actually the same. They have the matrices, the corresponding matrices will be the same if you write them down. And okay, now the classical control of a qubit is drawn in this way. Now, what this means is that we perform a measurement of this first qubit here, and then if the result was 1, then we we obtain the classical result, either 0 or 1. And if the result is 1, then we apply this unitary, the single qubit unitary on this qubit. And if the result was 0, we just do nothing. But in fact, it can be proved that these two operations together, they are actually equivalent to this circuit, to these operations. So in this circuit, we at first apply controlled, the quantum, just the quantum controlled version of U, as I defined before, and only then perform a measurement. So they are actually equivalent. And this is a very, very nice identity. And it is actually has its own name. It's called the principle of deferred measurement. So this means that we can postpone, actually, we can postpone the measurements to the end of the circuit. And it helps to analyze some hard algorithm and quantum protocols. Okay, I think I'll stop here this part of my lectures, and if there are any questions, I would be glad to answer.
So now there are no questions, and I think we can make a small break for 10 minutes. One question: can we have an access to this presentation somehow? Yeah, I think yes.
I don't think in real time. I think the organizers will publish it later, I think. Or I don't know how it can be accessed in real time.
I might have a small short question for the material.
Yes.
Can exploit in my right. So why is the so-called theorem so crucial for quantum computation and quantum circuits? So
well, because it limits our possibilities. So it is very easy to clone something classically and to copy something. But in the quantum world, if we have some unknown states, what we can do is we can measure it or apply some operation, unitary operation. And when we measure it, we change it. And so the measurement result is probabilistic. So if you heard something about a multiverse interpretation of quantum mechanics, after we measure the quantum states, we already choose only a single branch of multiverse. So we just can't go back. But if we have many copies of a single qubit unknown state, we can perform many measurements of them. And when we perform many measurements of the same copies of the single qubit state, we can know it. In general, we can reconstruct what the state was exactly, right? And without the possibility of cloning, when we don't have access to the copies, to the clones, we are limited in possibilities. Okay, I hope this answers.
Thanks.
So okay, now we have 8-minute break, and then we will return to your next lecture. Thank you.
Yes. What?